When we look up at the night sky with our naked eyes, we see a scattering of stars painted across a canvas of darkness. Yet what we perceive is only the faintest surface of a far deeper reality. Astronomers using powerful telescopes and sensitive instruments have long suspected that the visible matter in the universe is only a fraction of what is truly out there. The galaxies that shine, the stars that burn, and the gas that glows account for only a sliver of the total mass and energy budget. Something unseen, something that does not emit light, yet tugs gravitationally on everything around it, appears to dominate. This hidden presence is called dark matter, and it has forced scientists to reimagine the very structure of the cosmos. The story of dark matter begins almost a century ago. In the 1930s, Swiss astronomer Fritz Zwicky studied the Coma cluster, a vast collection of galaxies bound together in space. He carefully measured how fast the galaxies within the cluster were moving. According to the rules of Newtonian gravity, the visible matter in the galaxies should have been sufficient to calculate the gravitational pull that held the cluster together. But Zwicky realized the galaxies were moving too fast to be explained by the stars and gas he could see. If only visible matter were present, the cluster should have flown apart long ago. To account for this discrepancy, Zwicky proposed the existence of Dunkel Materie, or dark matter. His idea was radical, and at the time, many dismissed it. Yet his observations had revealed the first cracks in our assumption that light alone tells the whole story of the universe. For decades, the mystery lingered without resolution. Then, in the 1970s, astronomer Vera Rubin and her collaborator Kent Ford provided striking new evidence. They studied the rotation curves of spiral galaxies, including our own Milky Way. When stars orbit around the center of a galaxy, their speeds should decrease as one moves farther from the central mass, much as planets in the solar system move more slowly the farther they are from the sunday. But Rubin discovered that stars far from the galactic center were moving just as quickly as those near the core. The outer stars should have been slowed by gravity, yet they were not. The implication was inescapable. Galaxies are embedded in vast halos of invisible matter that outweigh the visible stars and gas many times over. Rubin's careful work turned dark matter from a curiosity into a central pillar of modern cosmology. Since then, the evidence has only grown stronger. One of the most compelling tools is gravitational lensing. According to Einstein's theory of general relativity, massive objects bend the path of light traveling near them. When light from a distant galaxy passes through a cluster of galaxies on its way to us, the invisible mass in the cluster distorts the light, magnifying and warping the image. By analyzing these distortions, astronomers can map the distribution of mass in the cluster, including the mass that does not emit light. Repeatedly, these maps have shown far more matter than what is visible. The unseen matter outweighs the stars and gas by large factors, sometimes by 5 or 6 times. The cosmic microwave background offers yet another line of proof. This faint afterglow of the Big Bang, first detected in 1965, encodes the conditions of the universe when it was only 380,000 years old. Subtle patterns in this radiation reveal how matter clumped together at that time. Modern satellites like the Wilkinson Microwave Anisotropy Probe and the Planck mission have mapped these patterns with exquisite detail. Their results show that ordinary matter, the protons, neutrons, and electrons that make up stars and planets, accounts for less than 15% of the matter content. The remaining 85% must be dark matter, exerting gravity but not interacting with light. Galaxy clusters further support this conclusion. When astronomers measure the hot X-ray emitting gas in clusters, they find that it is not sufficient to hold the clusters together. Only when dark matter is added to the equation do the dynamics make sense. Similarly, computer simulations of cosmic structure formation reveal that without dark matter, galaxies would never have formed in the way we observe them today. Gravity from ordinary matter alone would have been too weak to pull structures together quickly enough. Dark matter provided the hidden scaffolding that allowed stars, galaxies, and eventually life to emerge. The failure of ordinary matter and radiation to explain these observations is decisive. At first, one might suspect that gas or dust hidden from view could account for the missing mass. But careful surveys at many wavelengths, from radio waves to gamma rays, have shown that this is not the case. Even when astronomers tally up all the known baryonic matter, meaning the protons and neutrons in stars, planets, interstellar gas, and plasma, the total comes out far short of what is required. Dark matter is not simply ordinary matter hiding from view. It is something else, something that does not emit, absorb, or reflect light in any appreciable way. This realization poses one of the greatest puzzles in all of science. What is the nature of this invisible substance? Is it a new kind of particle beyond the standard model of physics? Could it be a population of primordial objects formed in the earliest instance of cosmic history? The stakes are enormous, for understanding dark matter means grasping the very fabric of the universe itself. And so, as the 20th century closed and the 21st began, scientists pressed forward with new theories, new instruments, and new hopes. The missing mass problem that Zwicky glimpsed in the Coma cluster and Rubin measured in galaxy rotations had become a global quest. Today, laboratories deep underground search for exotic particles, telescopes scan the skies for subtle distortions, and supercomputers simulate universes made of both visible and invisible matter. Yet despite these efforts, the identity of dark matter remains hidden. If unseen matter dominates the cosmos, it is natural to ask whether the most famous unseen objects of all, black holes, could provide the answer. Black holes are real, proven, and invisible to direct observation. They bend space, warp time, and trap light itself. Could it be that these enigmatic objects, long regarded as the most mysterious actors in astrophysics, are also the key to solving the mystery of dark matter? The night sky we observe tells only part of the story. To appreciate the scale of the hidden cosmos, imagine weighing a person, but only being able to count their bones, not their muscles or blood. You would quickly realize that what you see cannot explain their true weight. In much the same way, astronomers realize that what glitters in telescopes is not enough to explain the full mass of the universe. The invisible dominates the visible. This concept unsettled many at first, for it suggested that human senses, and even our most advanced instruments, were blind to the majority of reality. Yet as the data accumulated, skepticism gave way to acceptance. Consider the Bullet Cluster, a dramatic collision of two galaxy clusters about 3.8 billion light-years away. When these clusters collided, their hot gas clouds slammed into each other and slowed down, glowing brightly in X-rays. But the gravitational mass, traced by gravitational lensing of background galaxies, passed through almost unaffected. The visible matter lagged behind, while the unseen mass raced ahead. This cosmic experiment in nature revealed a direct separation between ordinary matter and the dominant invisible component. The Bullet Cluster has become one of the clearest demonstrations that dark matter exists independently of ordinary matter. It is not just a trick of modified gravity. Something real, unseen, and massive must be there. Such evidence builds a consistent picture. Without dark matter, the growth of galaxies and large-scale structures in the universe would make little sense. In the early universe, ordinary matter was coupled to radiation, and the pressure of photons resisted collapse. Only dark matter, immune to such pressure, could begin to clump and form gravitational wells. Later, ordinary matter fell into these wells, igniting star formation and eventually creating the galaxies we observe. Without dark matter, the universe would be a thin, diffuse soup, with no galaxies, no stars, and no life. In this way, dark matter is not merely an abstract concept, but the silent architect of cosmic history. The consensus that about 85% of the universe's matter is dark matter rests on multiple independent pillars: galaxy rotation curves, cluster dynamics, gravitational lensing, cosmic microwave background measurements, and structure formation simulations all converge on the same conclusion. When science reaches this kind of convergence from different methods, confidence grows. Still, confidence in existence does not mean understanding of identity. Knowing that dark matter is there is one thing, Knowing what it is made of is another. The simplest thought is that dark matter could be ordinary matter in disguise, like faint stars, brown dwarfs, or cold gas clouds. These possibilities, called massive compact halo objects, or MACHOs, were investigated through microlensing experiments. When a MACHO passes in front of a background star, its gravity briefly magnifies the star's light. Surveys monitoring millions of stars found some events, but not nearly enough to account for the required mass. Ordinary hidden matter cannot explain the majority of dark matter. Another possibility is that the laws of gravity need to be modified. If Newton's and Einstein's equations break down on galactic scales, perhaps the discrepancy could be explained without unseen matter. Modified Newtonian dynamics, proposed by Mordechai Milgrom in the 1980s, was one such attempt. While it could describe some galaxy rotation curves, it failed when confronted with the full range of evidence, especially the bullet cluster and the cosmic microwave background. As a result, the overwhelming majority of scientists favor the interpretation that dark matter is a real substance rather than a modification of gravity. Yet what kind of substance? Particle physics has proposed candidates like weakly interacting massive particles and axions. Experiments deep underground search for faint collisions of these particles with atomic nuclei. So far, however, no experiment has confirmed their existence. With every null result, the parameter space of possibilities shrinks. While this does not eliminate the particle hypothesis, it leaves the door open for alternative explanations. One alternative that has fascinated many researchers is the possibility that black holes themselves, especially primordial ones, might make up the dark matter. The reason black holes are so tempting is that they share a key property with dark matter. They interact primarily through gravity. They do not emit light. They are effectively invisible, except through their gravitational effects. Moreover, black holes are not hypothetical. We know they exist. We have observed stellar mass black holes in binary systems. We have measured stars orbiting the supermassive black hole in the center of our galaxy. We have even imaged the shadows of black holes using the Event Horizon Telescope. If invisible matter must exist, why not consider the most invisible objects of all? Of course, not all black holes are suitable candidates. Stellar mass black holes, those formed from dying stars, are too few to account for the required mass. Supermassive black holes, like Sagittarius A times, in the center of the Milky Way, dominate their local regions, but are again far too rare. To match the vast amounts of dark matter implied by cosmic measurements, one would need a population of black holes that permeate space in enormous numbers. This brings us to the concept of primordial black holes, objects that might have formed in the first moments after the Big Bang. Primordial black holes are hypothetical, but their existence is allowed by known physics. If density fluctuations in the early universe were large enough in certain regions, gravity could have overwhelmed pressure and collapsed matter directly into black holes. Unlike stellar black holes, which require the deaths of massive stars, primordial black holes could have formed long before stars existed. Their masses could range from smaller than asteroids to thousands of times the mass of the Sunday. If such a population exists, it could provide the hidden mass that has puzzled astronomers for nearly a century. The question then becomes how to test this possibility. Can we detect or rule out primordial black holes through their gravitational effects, through lensing events, or through signatures of Hawking radiation? Modern astronomy has taken up this challenge, deploying surveys and detectors across the electromagnetic spectrum and through gravitational waves themselves. The search is ongoing, and the debate is lively. What began as Zwicky's odd proposal and Rubin's careful measurement has expanded into one of the grandest quests in all of science. As we stand on the threshold of deeper exploration, we must ask ourselves a provocative question. If unseen matter dominates the cosmos, and if black holes are among the most convincing unseen objects we know, could it be that these two mysteries are in fact one and the same? The recognition of dark matter as the dominant form of matter in the universe has been one of the most humbling discoveries in the history of science. It reminds us that what is visible and familiar is not the whole of reality, but merely the tip of a cosmic iceberg. The luminous galaxies scattered across the sky, breathtaking though they are, represent only the glowing embroidery on a far larger, unseen fabric. In a sense, We live in a shadowed cosmos, where most of what is real refuses to reveal itself through light. As the evidence piled up through the late 20th century and into the 21st, cosmologists built a model of the universe that we now call the lambda-cold dark matter model. In this framework, the universe is composed of roughly 5% ordinary matter, about 27% dark matter, and about 68% dark energy. This picture fits a vast range of observations, from the cosmic microwave background to the distribution of galaxies on the largest scales. Yet while the model is enormously successful in describing the data, it is silent on the fundamental question of what dark matter actually is. The equations work, but the physical identity of the invisible component remains hidden. The human response to such ignorance is to search with greater determination. Across the world, massive detectors sit buried deep underground, shielded from cosmic rays, hoping to record a faint signal of a weakly interacting particle. Powerful accelerators like the Large Hadron Collider probe for new physics that might reveal dark matter candidates. Astronomical surveys sweep the skies, looking for subtle lensing events or unusual gamma-ray signals that might betray the presence of unseen objects. The ingenuity of these efforts is extraordinary, yet each new null result sharpens the enigma. We know the mass is there, we see its gravitational footprint, but we cannot yet touch it directly. This makes the suggestion that black holes could be involved all the more compelling. Black holes are not speculative, they are as real as the stars. When two black holes collide, the ripples they send through spacetime can be detected by observatories like LIGO and Virgo. When gas swirls around a supermassive black hole, it heats and shines with incredible brightness. When a star orbits close to one, its path betrays the black hole's presence. Yet the very thing that defines a black hole, the event horizon that traps all light, makes it invisible in the most literal sense. Black holes are the universe's natural dark objects. The possibility that black holes and dark matter might be connected is tantalizing, not because it is simple, but because it would unite two of the greatest mysteries in modern astrophysics. On one hand, we have dark matter, known only through its gravitational influence, invisible to every telescope. On the other hand, we have black holes, regions where gravity is so extreme that light itself cannot escape. Both are unseen, both are deeply gravitational, and both stand at the frontier of our knowledge. Could they in fact be the same phenomenon expressed in different ways? The road to answering this question requires caution. While imagination is essential in science, discipline and evidence must guide our steps. Black holes as dark matter is not the mainstream view, but neither is it dismissed outright. The idea must survive the gauntlet of observational tests, from microlensing surveys to cosmic background radiation studies. It must fit the structure of galaxies and clusters without breaking the delicate balance observed in the cosmos. And it must explain not only the existence of dark matter, but also the remarkable abundance and distribution inferred from multiple independent lines of evidence. What is at stake is nothing less than our understanding of the material content of the universe. If dark matter turns out to be made of exotic particles, then the triumph will belong to particle physics, revealing new laws of nature beyond the standard model. If, on the other hand, black holes turn out to play a significant role, the triumph will belong to astrophysics, showing that the seeds of darkness were sown in the earliest instance of cosmic time. Either path would reshape our understanding of the universe's origin, evolution, and ultimate fate. For the moment, we stand in the middle of this mystery, aware of the invisible mass, yet ignorant of its form. What Zwicky glimpsed in the 1930s, and Rubin confirmed in the 1970s, has grown into one of the greatest scientific quests of all time. The journey ahead promises discoveries that will challenge our imaginations, and perhaps redefine our place in the cosmos. And so the question emerges with new clarity. If unseen matter dominates the universe, and if black holes are the most powerful unseen objects we know, then perhaps these two enigmas are bound together. To explore that possibility, we must turn from the evidence of dark matter to the story of black holes themselves, tracing their path from theory to undeniable reality. The idea of a black hole may feel like a product of modern science fiction, but its roots stretch back more than 2 centuries. In the late 18th century, English natural philosopher John Michel and French mathematician Pierre-Simon Laplace both speculated about the existence of what they called dark stars. They reasoned that if an object were massive enough, its gravity could be so strong that light itself could not escape. Though their arguments were couched in the language of Newtonian physics, the essence of the idea was startlingly similar to what we now recognize as a black hole. These early musings faded into obscurity because light was thought to be a wave rather than a particle, and the notion of trapping light felt abstract and improbable. Yet the seed had been planted. The true theoretical foundation for black holes emerged in the early 20th century with Albert Einstein's general theory of relativity. In 1916, only months after Einstein published his equations, German physicist Karl Schwarzschild found an exact solution that described the gravitational field outside a perfectly spherical mass. This solution implied the existence of a boundary, now called the Schwarzschild radius, within which nothing, not even light, could escape. The mathematics was clear, but for decades, many doubted that such objects could exist in reality. Even Einstein himself remained skeptical, believing that some unknown mechanism would prevent complete collapse. For much of the 20th century, black holes were regarded as mathematical curiosities rather than astrophysical objects. Yet, as observations improved, the evidence began to mount that nature might indeed create such extreme environments. The collapse of massive stars offered the most natural pathway. When a star many times heavier than the Sun exhausts its nuclear fuel, the outward pressure that counteracts gravity vanishes. The star's core implodes, and depending on its mass, it may form a neutron star, or, if massive enough, a black hole. These stellar mass black holes should exist throughout the galaxy, invisible themselves, but detectable through the behavior of their surroundings. By the mid-20th century, astronomers began to uncover strange, cosmic sources that hinted at extraordinary compactness. Quasars, discovered in the 1960s, shone with the brilliance of entire galaxies, yet came from regions no larger than our solar system. The most plausible explanation was accretion of matter onto supermassive black holes, releasing staggering amounts of energy as gas spiraled inward and heated to extreme temperatures. Though controversial at first, this interpretation gained strength as evidence accumulated. Closer to home, stellar mass black holes revealed themselves in binary star systems. When a black hole orbits a normal star, it can siphon material from its companion, forming an accretion disk that glows in X-rays. Systems such as Cygnus X1 provided the first robust candidates for black holes. The motions of the companion stars indicated invisible partners far too massive to be neutron stars, pointing squarely to the existence of black holes. The X-ray sky, once mysterious, became a laboratory for studying these unseen objects. At the centers of galaxies, even more massive black holes lurk. Our own Milky Way hosts Sagittarius A*, a supermassive black hole containing about 4 million times the mass of the Sunday. The orbits of stars near this hidden giant have been tracked with exquisite precision, showing them whipping around an invisible point with speeds of thousands of kilometers per second. No ordinary cluster of stars could produce such motion. Only a supermassive black hole provides a consistent explanation. Similar evidence has emerged from other galaxies, suggesting that nearly every large galaxy harbors a central black hole, millions or billions of times more massive than the Sunday. Intermediate mass black holes, bridging the gap between stellar mass and supermassive varieties, have proven harder to pin down. Hints of their presence come from unusually dense star clusters and from gravitational wave signals detected by LIGO and Virgo. While not yet as firmly established as their smaller and larger cousins, these intermediate black holes may provide clues to how the giant black holes in galactic centers first grew. The possibility that black holes exist across a wide spectrum of masses deepens our appreciation of their role in cosmic history. The ultimate confirmation of black holes has come through multiple revolutionary observations. In 2015, the LIGO collaboration announced the first detection of gravitational waves, ripples in space-time predicted by Einstein a century earlier. The signal came from two black holes merging more than 1 billion light-years away. The detection was a triumph, not only for experimental ingenuity, but also for the reality of black holes themselves. Since then, dozens of mergers have been recorded, revealing a rich population of black holes in the universe. Even more dramatic was the achievement of the Event Horizon Telescope, an Earth-sized network of radio telescopes. In 2019, the collaboration released the first direct image of a black hole's shadow, the supermassive giant at the heart of galaxy M87. The dark silhouette against a glowing ring of hot gas confirmed the predictions of general relativity in a regime never before tested. 3 years later, the same technique revealed the shadow of Sagittarius A*, the black hole at the center of our Milky Way. For the first time, humanity could see the unseeable. From 18th century speculations about dark stars to 21st century images of cosmic shadows, the journey of black holes has been one of the most dramatic sagas in science. What was once dismissed as impossible is now central to our understanding of galaxies, stellar evolution, and the dynamics of the universe. Black holes are no longer mathematical curiosities. They are real, they are common, and they shape the cosmos in profound ways. The question now facing us is whether these known populations of black holes, stellar, intermediate, and supermassive, could also be the long-sought missing matter. They are invisible, they are massive, and they exert pure gravity. Yet, are they numerous enough to account for the vast reservoir of unseen mass revealed by cosmology? To answer this, we must turn to the idea of primordial black holes, relics of the early universe that may still roam the cosmos today. As the evidence for black holes grew stronger, their presence in both the small and the large scales of the cosmos reshaped astronomy. They were no longer rare or exotic, but essential actors. The challenge then became not simply proving their existence, but understanding their diversity and origins. Stellar mass black holes, formed from the death throes of massive stars, are sprinkled throughout galaxies. Their births are tied to the cycle of stellar evolution, to the supernova explosions that enrich the cosmos with heavy elements, and to the balance between nuclear fusion and gravitational collapse. Every black hole of this kind is a silent monument to a star that once blazed with light and ended in implosion. Supermassive black holes, by contrast, dwell in the cores of galaxies like ancient monarchs. Their masses, ranging from millions to billions of times the mass of the Sun, make them the most dominant single objects in galactic centers. Astronomers puzzled for decades over how such titans could form. Did they grow gradually from smaller stellar mass seeds, consuming gas and merging with others over billions of years? Or did some form already massive in the infancy of the universe, perhaps through the direct collapse of enormous clouds of primordial gas? The early appearance of quasars less than 1 billion years after the Big Bang suggests that supermassive black holes must have grown quickly, a fact that continues to challenge theorists. Intermediate mass black holes occupy the middle ground, a mass range from hundreds to hundreds of thousands of suns. Their existence is not yet proven with the same certainty, but growing evidence points toward them. Some ultraluminous X-ray sources may be powered by accretion onto intermediate black holes. Some dense star clusters appear to be anchored by objects too heavy to be stars, but too light to be supermassive giants. And the gravitational wave signals detected in recent years include black hole mergers heavier than expected from normal stellar evolution, hinting that intermediate black holes may indeed populate the universe. The catalogue of known black holes has expanded through a variety of ingenious detection techniques. In X-ray binaries, the black hole's presence is betrayed by hot gas spiraling inward from a companion star. In galactic centers, the rapid orbits of nearby stars trace out the invisible mass they encircle. Gravitational waves reveal the collisions of pairs of black holes, each event sending ripples that momentarily stretch and squeeze the fabric of space on Earth. Even microlensing, the temporary brightening of distant stars as a massive object passes in front, can in principle reveal isolated black holes wandering the galaxy. In every case, we see not the black hole itself, but its influence on its surroundings. The accumulation of such observations has transformed black holes from theoretical oddities into established members of the cosmic family. They are now woven into our understanding of astrophysics. When we simulate galaxies forming on supercomputers, we must include the influence of supermassive black holes, driving powerful jets and winds that regulate star formation. When we model stellar evolution, we must account for which stars will end as neutron stars and which will collapse further into black holes. Even the detection of heavy elements in the universe is linked to the role of black holes, since many are born in violent supernovae that forge and scatter these elements into space. Yet the fascination of black holes does not lie only in their astrophysical importance, but also in their nature as extreme laboratories of physics. Near their event horizons, the predictions of general relativity are tested in ways impossible to replicate on Earth. Time dilation, gravitational redshift, and the warping of spacetime reach their most dramatic expressions. The merging of black holes produces gravitational waves that carry information about spacetime itself. In this way, black holes are not only objects to be catalogued, but also tools to probe the deepest laws of the universe. It is worth remembering that the journey from skepticism to certainty took decades. In the early days of relativity, even Einstein doubted the existence of black holes, suspecting that some mechanism would prevent collapse to a singularity. Many physicists considered them too strange to be real. Only the accumulation of hard evidence, from the X-ray sky to stellar orbits to gravitational waves, forced the scientific community to accept them as facts. This progression illustrates the resilience and humility of science. Ideas may begin as speculation, face resistance, and eventually triumph when the data demands it. Today, the discussion has moved beyond whether black holes exist to what roles they play in cosmic evolution and whether they could be linked to other great mysteries. Could black holes help explain how galaxies formed so early in the universe? Could they be connected to the mysterious dark energy that drives cosmic acceleration? And most relevant to our story, could they account for some or all of the missing dark matter that permeates the cosmos? We know the varieties of black holes that form from stellar death or dwell in galactic centers. We know they are real and powerful, but the question of whether they are numerous enough to explain the dark matter remains unanswered. To explore that possibility, we must turn not to the familiar black holes of collapsed stars or galactic cores, but to the more exotic possibility of black holes born in the very first moments after the Big Bang. These primordial black holes, if they exist, would provide a bridge between the two great mysteries, the enigma of dark matter and the physics of the early universe. The progress from speculation to certainty in the study of black holes has been one of the most remarkable scientific journeys of the modern era. What began as a mathematical oddity in the equations of general relativity has become an observational reality, confirmed again and again by independent lines of evidence. No longer do scientists ask whether black holes exist. The question has shifted to how many there are, how they form, and how they influence the universe on every scale. Consider the two great milestones of the past decade. The detection of gravitational waves by LIGO and Virgo opened an entirely new window on the cosmos. For the first time, we could hear the universe, registering the faint vibrations of space-time itself. The very first detection in 2015 came from the merger of two black holes more massive than any known from X-ray binaries. Since then, dozens of additional events have been recorded, revealing a population of heavy black holes that surprised theorists. These discoveries hint that our understanding of stellar evolution may be incomplete, or that black holes form in ways not yet fully recognized. Each signal carries with it a story from billions of years ago, written in the trembling fabric of space. The second milestone was the imaging of black hole shadows by the Event Horizon Telescope. The ring of light around the central black hole in galaxy M87, and later around Sagittarius A times in our own Milky Way, offered a visual confirmation of the predictions of relativity. The dark silhouette against the glowing accretion flow was unlike anything previously captured. For the first time, we had not only indirect evidence, but also direct images of the regions where space-time collapses upon itself. The cultural impact of these images was enormous, symbolizing humanity's ability to reach across unimaginable distances to glimpse the most extreme environments in existence. Together, Gravitational wave astronomy and horizon-scale imaging have transformed black holes from abstract concepts into tangible objects of study. We now measure their masses, spins, and merger rates. We watch their shadows flicker as hot gas orbits close to the point of no return. We calculate their role in shaping galaxies and clusters. The invisible has become quantifiable. Yet this very success invites a new question. If black holes are real, common, and invisible, could they also provide the solution to the enigma of dark matter? The idea is attractive for its simplicity. Unlike exotic particles that require new physics, black holes are already part of the established framework of general relativity. They possess the very properties demanded of dark matter. They interact primarily through gravity. They do not emit light, and they can persist over cosmic timescales. If there were enough of them scattered throughout the universe, they could in principle account for the hidden mass. The known populations of stellar and supermassive black holes cannot do so, as they are too rare. But what if there exists another population, one born not from stars, but from the early universe itself? This is where the hypothesis of primordial black holes enters the story. These hypothetical objects would have formed in the chaotic first fractions of a second after the Big Bang, collapsing from regions where density fluctuations were high enough to overwhelm expansion and pressure. Unlike stellar black holes, their masses could span an enormous range, from less than a gram to thousands of times the mass of the Sunday. Some would have evaporated through Hawking radiation, but others, depending on their mass, could still persist today. If such a population exists in the right numbers and masses, it could provide the missing dark matter. The notion of primordial black holes connects two frontiers at once. On one side is cosmology, with its puzzles of dark matter and the structure of the universe. On the other side is the physics of the early cosmos, where inflation, quantum fluctuations, and high-energy processes shaped the primordial soup. If primordial black holes are real, they would be fossils of those earliest times, carrying information about conditions otherwise beyond our reach. Their discovery would revolutionize both astrophysics and particle physics. Of course, the leap from known black holes to primordial ones requires careful testing. Observational campaigns must search for signs of their presence, from microlensing of background stars to the imprint they might leave on the cosmic microwave background. Gravitational wave detectors may capture the echoes of their mergers, revealing whether unusual populations exist. Gamma-ray observatories look for the telltale signature of evaporating small black holes. Each method provides a different perspective, together forming a network of tests that can confirm or constrain the hypothesis. As the 20th century turned into the 21st, the scientific community embraced the challenge. If dark matter is not made of particles we can detect in laboratories, perhaps it is made of objects we can detect in the sky. Black holes, once dismissed as theoretical oddities, now stand as real and measurable. And among them, the primordial variety may hold the key to one of the deepest mysteries of all. Thus, the journey from Mitchell's dark stars to Einstein's skepticism, from X-ray binaries to the Event Horizon Telescope, sets the stage for the next chapter. We have learned that black holes are real, abundant, and profoundly influential. Now we must ask whether they existed before stars, before galaxies, before any ordinary structures, as relics of the Big Bang itself. Could primordial black holes be the hidden substance that has shaped the cosmos from the very beginning? To explore that question, we must venture into the earliest instance of time, when the universe was young, dense, and wild. The early universe was a place of unimaginable density and heat, a churning cauldron where the laws of physics were stretched to their limits. In the first fractions of a second after the Big Bang, energies were so intense that matter and radiation were nearly indistinguishable. Quantum fluctuations, the tiny jitters of uncertainty that rule the microscopic world, were magnified by cosmic inflation, a brief but astonishing period of rapid expansion. Out of these fluctuations, the seeds of cosmic structure were sown. The galaxies we see today, the stars that shine, and the planets that orbit them all, trace their origins to these minute irregularities in the primordial fireball. But some scientists have asked a more provocative question. Could these early fluctuations have given rise not only to galaxies billions of years later, but also to black holes within the first instance of cosmic history? The concept of primordial black holes emerges naturally from this idea. If certain regions of the early universe were denser than their surroundings, gravity could have overwhelmed the pressure of radiation and forced collapse into black holes. Unlike stellar black holes, which are born from the deaths of massive stars, these would have formed long before the first stars ever ignited. Their masses could vary across an astonishing range. Some might be as light as mountains, others as heavy as thousands of suns. Their diversity would reflect the spectrum of fluctuations present in the infant cosmos. The conditions of the early universe provided multiple mechanisms by which primordial black holes could arise. During inflation, tiny quantum fluctuations were stretched to cosmic scales. In some regions, these fluctuations may have been strong enough to create overdensities that later collapsed. Other scenarios involve phase transitions, moments when the universe cooled and fundamental forces separated from one another. Just as water freezes into ice and forms cracks, the universe's cooling could have produced irregularities that seeded black holes. Even topological defects like cosmic strings, hypothetical relics of high-energy physics, have been proposed as possible triggers for primordial collapse. If primordial black holes did form, their survival depends on their mass. In the 1970s, Stephen Hawking made the extraordinary prediction that black holes are not entirely black. Quantum effects near the event horizon should allow them to emit radiation, slowly losing mass in the process. This Hawking radiation is imperceptible for stellar or larger black holes, but for very small ones, it could be dramatic. Black holes with masses less than about 10 to the power of 15 grams would have evaporated by now, disappearing in bursts of high-energy particles. Heavier primordial black holes, however, could survive to the present day. These survivors, roaming silently through space, could be abundant enough to account for dark matter. The appeal of primordial black holes as dark matter candidates lies in their familiarity. Unlike exotic new particles, they require no extension of the standard model of physics. They are predictions of general relativity, combined with known conditions of the early universe. If they exist, they would elegantly solve the missing mass problem without invoking unseen particles. Moreover, they might help explain puzzles such as how supermassive black holes formed so quickly in the early universe. If primordial black holes provided seeds, galaxies could have grown around them in rapid time. The idea is not new. In the 1970s, when Hawking and others considered the implications of his radiation, primordial black holes were proposed as a possible dark matter candidate. For a time, interest waned as attention shifted toward weakly interacting massive particles, which seemed promising from the perspective of particle physics. But as decades of experiments failed to reveal such particles, the primordial black hole hypothesis has experienced a revival. Advances in gravitational wave astronomy, microlensing surveys, and cosmic background measurements have given scientists new ways to test the idea. What was once a fringe speculation has re-emerged as a serious contender. Still, the notion of black holes born in the Big Bang stretches the imagination. To picture it, imagine a universe less than a second old, filled with searing radiation and rapidly expanding space. Amid the chaos, some regions are just a bit denser than others. Gravity in those patches pulls inward, overwhelming the outward push of pressure. In an instant, the matter collapses beyond its Schwarzschild radius, forming a black hole. Unlike the black holes formed billions of years later from dying stars, these are children of the cosmos itself, fossils of creation. They would carry within them the memory of conditions far beyond the reach of any laboratory experiment. If primordial black holes exist, their presence would connect the physics of the smallest scales to the largest structures in the cosmos. Quantum fluctuations, normally confined to the subatomic world, would have been frozen into black holes massive enough to bend light and shape galaxies. This connection is one of the most profound in science, bridging quantum mechanics, general relativity, and cosmology. It transforms the mystery of dark matter from a question about invisible particles into a question about the birth of the universe itself. Yet extraordinary ideas demand extraordinary evidence. The next step in our journey is to ask how we might detect these relics, how to distinguish them from other possibilities, and what constraints observations already provide. The search for primordial black holes is not only a quest to solve the dark matter puzzle, but also a way to peer back into the first moments of time. The conditions required to create primordial black holes are extreme but not impossible. Inflation, that brief epoch when the universe expanded faster than the speed of light itself, set the initial stage. Inflation smoothed the cosmos on large scales, but it also magnified tiny quantum fluctuations into real density variations. These variations became the seeds of all later cosmic structure. For the most part, they were small, leading to the gradual formation of galaxies over billions of years. But if inflation produced rare, larger fluctuations, those regions could have collapsed into black holes almost instantly. In this way, the ghostly whisper of quantum uncertainty might have given birth to some of the heaviest objects in existence. Different scenarios for primordial black hole formation predict different mass ranges. If the collapse occurred at extremely early times, the resulting black holes would be tiny, perhaps no heavier than a mountain. If it occurred later, after the universe had expanded and cooled somewhat, the black holes could be thousands of times heavier than the Sunday. The diversity of possible masses makes primordial black holes an unusually flexible hypothesis. It allows them to be considered as dark matter candidates across a wide swath of possibilities, depending on how the early universe unfolded. Yet the survival of such objects depends critically on Hawking radiation. According to Hawking's theoretical insight, black holes lose mass over time by emitting faint radiation. The smaller the black hole, the faster the process. A black hole weighing less than about 10 to the power of 15 grams would have evaporated entirely within the age of the universe. Such black holes, if they formed, might have vanished long ago, leaving behind only bursts of high-energy particles at their final moments. Heavier primordial black holes, however, would endure, and it is these survivors that remain interesting as possible dark matter candidates. The possibility that small primordial black holes could have evaporated raises fascinating questions. If they did exist and disappear, their final explosions might have contributed to the cosmic gamma-ray background or left subtle imprints in the early universe's light. Detecting such signatures would be indirect evidence of their existence. On the other hand, the absence of such signatures places limits on how abundant they could have been. In this way, even the search for their ashes constrains the hypothesis. Primordial black holes also intersect with the mystery of supermassive black hole formation. Astronomers have discovered quasars powered by billion solar mass black holes, less than 1 billion years after the Big Bang. How did such giants grow so quickly? One possibility is that they were seeded by primordial black holes, already massive at birth, which provided a head start. This idea offers an elegant bridge between two puzzles: the nature of dark matter and the rapid emergence of supermassive black holes. If true, primordial black holes would not only explain the missing mass, but also account for the astonishingly fast appearance of the universe's earliest beacons. The history of this hypothesis reflects the ebb and flow of scientific fashion. In the 1970s, interest was high, spurred by Hawking's work and the recognition that primordial black holes might have unique signatures. By the 1990s, focus had shifted toward particle candidates like weakly interacting massive particles, motivated by extensions of the standard model of particle physics. The appeal of new physics and the hope of laboratory detection made particles the favored explanation for decades. But as experiment after experiment returned null results, attention began to drift back toward astrophysical alternatives. In the past decade, advances in gravitational wave astronomy and large-scale surveys have renewed interest in primordial black holes, placing them back on the table as a viable, if constrained, possibility. Part of the allure of primordial black holes lies in their testability. Unlike hypothetical particles that interact only through forces we cannot easily measure, black holes have clear gravitational effects. They can bend light through lensing, disturb stellar motions, merge in detectable gravitational wave events, and potentially radiate at the end of their lives. Each of these phenomena provides a pathway to confirm or deny their existence. This makes them attractive targets for observational campaigns, which thrive on measurable consequences. Still, the idea remains controversial. To many physicists, the elegance of new particle candidates, tied to deeper theories like supersymmetry or the strong CP problem, remains compelling. To others, the absence of detection argues for exploring every possibility, including those that once seemed speculative. This tension drives progress. Competing ideas sharpen the focus of inquiry, and the truth will be revealed only through evidence. To grasp the stakes, imagine that primordial black holes are confirmed as the dark matter. Such a discovery would revolutionize both astrophysics and cosmology. It would mean that the missing mass is not a new particle at all, but a population of ancient objects formed in the universe's first heartbeat. It would link the smallest scales of quantum fluctuations to the largest scales of cosmic structure. And it would remind us that the universe is capable of producing wonders that stretch the imagination far beyond the boundaries of human intuition. Yet, imagination alone is not enough. We must ask how to find them, how to separate their possible signatures from the background noise of the cosmos, and what the current data already tells us. This brings us to the observational frontier, where telescopes, detectors, and satellites seek the footprints of primordial black holes across the universe. The story of primordial black holes has unfolded in waves, reflecting the evolving landscape of science itself. When the idea was first raised in the 1970s, it emerged at the intersection of cosmology and quantum theory, inspired by the recognition that gravity could dominate in regions of the early universe where density was unusually high. The novelty of Hawking radiation gave these hypothetical objects an added intrigue. If very small black holes had formed, they might now be exploding in brilliant gamma-ray bursts. The search for such signals galvanized the scientific community for a time, but as data failed to provide clear evidence, enthusiasm waned. The field's attention shifted toward particle physics, where new theories offered elegant solutions to both dark matter and other unresolved puzzles. For decades, the majority of effort went into hunting for weakly interacting massive particles, axions, and sterile neutrinos. Vast underground laboratories filled with ultra-pure detectors were built to capture the faintest whispers of new particles. Particle colliders probed higher energies in the hope that something unseen would materialize. The gravitational role of primordial black holes was not abandoned, but it became a quieter line of investigation, overshadowed by the bright promise of particle discoveries. But science is relentless in following the evidence. As the years turned into decades, and one experiment after another returned null results, the balance of interest began to shift. The silence of the underground detectors forced physicists to reconsider. Perhaps dark matter was not a particle we could catch, but an astrophysical population we could infer. At the same time, advances in observational astronomy provided new tools. The rise of gravitational wave detectors allowed astronomers to listen to the universe in a new way, and their very first detections hinted at populations of black holes heavier than expected from stellar evolution. Surveys of the sky with ever greater sensitivity allowed astronomers to probe microlensing events, searching for dark, compact objects passing in front of stars. The cosmic microwave background, measured with exquisite precision, gave new constraints on how matter behaved in the early universe. The convergence of these tools created a fertile ground for the revival of the primordial black hole idea. The renewed interest has been marked not by uncritical enthusiasm, but by sober evaluation. Every observational test constrains the hypothesis, eliminating some mass ranges while leaving others viable. Microlensing experiments have shown that primordial black holes cannot make up all of dark matter in certain ranges, such as masses comparable to the Earth. The absence of gamma-ray bursts argues against a large population of tiny evaporating black holes. Yet in other windows, especially around tens of solar masses, and in some intermediate ranges, the possibility remains open. It is in these gaps that researchers now focus their attention, carefully balancing what is allowed with what is excluded. Primordial black holes have also gained attention because of their potential to connect multiple mysteries. Not only could they explain the missing dark matter, but they could also serve as seeds for the rapid formation of supermassive black holes as anchors for early galaxy growth and as potential sources of unusual gravitational wave events. This convergence of explanatory power makes them a tantalizing candidate. Even if they do not account for all of dark matter, their existence in some abundance could still reshape our understanding of cosmic history. The revival of interest is also a reminder of how science works. Ideas are proposed, tested, set aside, and sometimes resurrected when new evidence or new technologies make them relevant again. Primordial black holes exemplify this cycle. They were once considered fringe, nearly forgotten in the rush toward particle physics. Now they stand once again in the spotlight, not because of speculation alone, but because the weight of null results elsewhere has demanded alternative thinking. In this way, they embody the resilience of scientific inquiry, which always adapts to what the data allows. Still, the challenge remains immense. Proving the existence of primordial black holes requires more than consistency with observations. It requires direct signatures, unmistakable footprints that cannot be explained by anything else. The next chapters in this story will involve examining how astronomers search for such signatures, what constraints have already been drawn, and what future instruments may finally answer the question. For now, the idea remains alive that in the very first instance of the universe, before stars, before galaxies, before even atoms fully formed, gravity may have sculpted regions of space into black holes. If true, those ancient relics still wander the cosmos today, invisible to our eyes, but perhaps holding the key to the greatest mystery of all, the missing mass that outweighs every star and planet combined. And so we arrive at a new frontier. The hypothesis of primordial black holes has been defined and motivated. The question now is how to test it. What evidence would confirm or refute the existence of these ancient objects? To answer, we must leave theory behind and turn to the realm of observation, where telescopes, detectors, and satellites scan the heavens for traces of the invisible. The great strength of science is that bold ideas must ultimately face the tribunal of evidence. The hypothesis of primordial black holes as dark matter is elegant in theory, but it can only endure if observations permit it. Over the past several decades, astronomers have deployed ingenious methods to search for these elusive objects. Some of these methods have returned tantalizing hints. Others have imposed strict limits, and together they have begun to carve away at the once wide-open landscape of possibilities. The story of these searches is not one of disappointment, but of refinement, as each experiment narrows the field and sharpens the questions. One of the most direct approaches relies on the phenomenon of gravitational microlensing. When a massive object passes between Earth and a distant star, its gravity bends the light, temporarily magnifying the star's brightness. The duration of the brightening depends on the mass of the intervening object. For decades, astronomers have monitored millions of stars, particularly in the direction of the Large Magellanic Cloud and the galactic bulge, to catch such fleeting events. Collaborations like MACHO, IROS, and OGLE pioneered these surveys, and more recently the Subaru Hyper-SuPrimeCam has carried the torch with higher sensitivity. What they have found is illuminating. Some microlensing events have indeed been recorded, confirming the presence of compact objects like faint stars, brown dwarfs, and possibly black holes in the galactic halo. But the number of such events falls far short of what would be required if dark matter were composed entirely of primordial black holes in certain mass ranges. These results have effectively ruled out primordial black holes as the dominant form of dark matter across wide swaths of possible masses, especially those comparable to planets or small stars. Yet the constraints are not uniform. Gaps remain where black holes of particular masses could still hide undetected, waiting for more sensitive surveys to reveal them. A second avenue of evidence comes from the ripples of space-time themselves. The detection of gravitational waves from merging black holes has opened a revolutionary window. The first event, detected in 2015, involved two black holes of about 30 solar masses each, heavier than most expected from normal stellar evolution. This immediately sparked speculation. Could these be primordial black holes? Subsequent detections of similarly massive black holes kept the question alive. While stellar processes can in principle produce such objects, the unexpected abundance raised eyebrows. If primordial black holes contribute significantly to the population of merging pairs, gravitational wave observatories might be hearing their signatures. At the same time, the rate and distribution of events provide constraints. If primordial black holes were too numerous, the sky would resound with far more mergers than we currently detect. The cosmic microwave background, the afterglow of the Big Bang, offers another test. Primordial black holes accreting gas in the early universe would have injected energy into the surrounding plasma. This process would have altered the subtle anisotropies of the microwave background, leaving fingerprints in its temperature and polarization patterns. Satellites like WMAP and Planck have measured these patterns with extraordinary precision, and their results limit how many primordial black holes could have existed in certain mass ranges. Too many would have distorted the cosmic background beyond what is observed. Closer to home, astronomers have looked at the dynamics of wide binary stars in our galaxy. These fragile pairs, orbiting each other at large separations, can be disrupted if heavy compact objects frequently pass nearby. By studying the survival of such binaries, researchers place limits on how many massive intruders can populate the galactic halo. Similarly, the structure of star clusters and dwarf galaxies provides constraints. If too many black holes roamed within them, their gravitational influence would have torn apart the delicate stellar arrangements we see today. High-energy astrophysics offers yet another set of clues. Small primordial black holes evaporating through Hawking radiation would produce gamma rays. The absence of an excess in the gamma ray background places strong bounds on the abundance of such tiny relics. Instruments like NASA's Fermi Gamma Ray Space Telescope have combed the skies, and their data shows that primordial black holes below a certain mass threshold cannot make up the dark matter. Even cosmic ray detectors searching for anomalous particles contribute to this picture, tightening the web of constraints. Each of these approaches, microlensing, gravitational waves, cosmic background measurements, stellar dynamics, and high-energy observations, acts like a sieve, filtering out what is impossible and leaving behind what might still be true. The space of possibilities has shrunk, but it has not disappeared. There remain windows where primordial black holes could plausibly account for a significant fraction of dark matter. These windows lie mostly in the mass ranges around tens of solar masses, and in certain intermediate ranges, where current instruments have limited sensitivity. The picture that emerges is neither a triumphant confirmation nor a decisive refutation. Instead, it is a nuanced landscape of constraints and opportunities. Science often progresses this way, by ruling out the impossible and clarifying the possible. The hypothesis of primordial black holes has survived this gauntlet, not intact, but not destroyed either. It remains alive in the narrow corridors left open by data, corridors that new generations of instruments are now poised to explore. The question now is how much longer those corridors will remain open. As telescopes and detectors grow more sensitive, the surviving windows shrink. The next decade will likely prove decisive. Either primordial black holes will be discovered within the allowed ranges, or the hypothesis will be forced into obscurity. For now, the evidence is ambiguous, the debate lively, and the stakes enormous. The hunt for primordial black holes has become a detective story told across the sky. Each observational method contributes a piece of the puzzle, and together, they form a network of evidence that strengthens or weakens the case. Perhaps the most striking twist in this story came with the dawn of gravitational wave astronomy. When LIGO first detected a chirp in September of 2015, the signal lasted only a fraction of a second, but it was enough to reveal a collision of two black holes, each roughly 30 times the mass of the Sunday. Before that moment, most known stellar black holes, identified in X-ray binaries, clustered around 10 solar masses. Black holes as heavy as 30 solar masses seemed unusual. Suddenly the community wondered, could these be primordial? Some theorists argued that if black holes formed in the early universe, they could naturally populate this mass range and survive to the present, merging occasionally and producing exactly the kind of signal that LIGO detected. As more detections rolled in, the discussion deepened. LIGO and its partner Virgo recorded dozens of black hole mergers, revealing a population of unexpectedly massive objects. Some were more than 50 solar masses, even pushing toward 100. While models of stellar evolution can explain some heavy black holes, particularly in regions with very low metallicity where stars lose less mass through winds, the abundance still felt surprising. If even a fraction of these were primordial, it would reshape the dark matter debate. Yet the rate of detections also imposes limits. If primordial black holes made up all of dark matter in that mass range, mergers would be far more common than observed. Thus, the gravitational wave data cuts both ways. It raises intriguing possibilities, but also narrows what is allowed. Meanwhile, microlensing surveys have continued to refine their results. The MACHO project, active in the 1990s, monitored stars in the Large Magellanic Cloud, searching for temporary brightening events. It detected some candidates, but not nearly enough to explain all of the dark matter. The EROS and OGLE collaborations, with larger datasets and improved analysis, confirmed the shortfall. More recently, the Subaru Hyper SuPrimeCam on Mauna Kea extended these searches, probing smaller mass ranges with higher sensitivity. Its results ruled out significant populations of primordial black holes across wide intervals, though once again leaving narrow mass windows where they could still lurk. Microlensing is powerful, but it is not omnipotent. Some ranges are inherently difficult to probe because events are too short or too rare to catch reliably. The cosmic microwave background provides a more subtle but equally powerful constraint. If primordial black holes were abundant and heavy, they would have accreted matter in the early universe. This accretion would release radiation, heating the surrounding plasma and altering the ionization history. Such changes would leave measurable imprints in the microwave background's delicate anisotropies. Observations from the WMAP and Planck satellites, which map the sky with exquisite precision, show no such distortions beyond what the standard model predicts. This absence rules out large numbers of primordial black holes in certain mass ranges, especially those heavier than 1,000 suns. The early universe itself therefore acts as a laboratory, its fossil light recording what kinds of dark matter could or could not exist. Closer to our galaxy, the behavior of stars provides another form of evidence. Wide binary stars, pairs bound by gravity but separated by vast distances, are exquisitely sensitive to perturbations. A close encounter with a heavy black hole could disrupt their fragile orbits. By studying how many such binaries survive in the galactic halo, astronomers can place upper limits on how often such encounters occur, and therefore how many black holes of a given mass can exist. Similarly, the stability of dwarf galaxies and star clusters offers another check. If primordial black holes were too common, their gravitational nudges would have torn apart these systems long ago. The fact that we still see them intact is itself a silent testimony against an overabundance of massive intruders. At the opposite extreme, the smallest primordial black holes would reveal themselves not through gravity, but through their evaporation. Hawking's prediction of radiation implies that tiny black holes should have fizzled away over cosmic time, but those on the cusp of evaporating today could release bursts of high-energy gamma rays. Instruments like the Fermi Gamma Ray Space Telescope watch for such signals, and their absence rules out certain populations. Even the diffuse glow of gamma rays across the sky constrains how many such black holes could have existed, for their combined evaporation would have left a visible mark. When all of these strands are woven together, the tapestry is complex but coherent. Primordial black holes cannot make up all of dark matter across most mass ranges. Yet narrow windows remain, especially for black holes of tens of solar masses and in certain intermediate ranges. These are the corridors where the hypothesis still survives. They are slim but significant, and they motivate continued searching. In science, survival through constraint is often as important as outright discovery, for it guides the focus of future experiments and tells us where to look next. The next frontier lies in expanding these observational tests with new tools. Gravitational wave detectors are being upgraded to increase sensitivity, promising to catch fainter and more distant mergers. New microlensing surveys with larger fields of view will probe shorter events and smaller masses. Future cosmic microwave background missions will sharpen constraints with even greater precision. Each of these instruments will either squeeze the windows tighter or perhaps, just perhaps, catch the first unmistakable signs of primordial black holes. The cumulative weight of these observations paints a picture both sobering and hopeful. On one hand, the vast landscape of possibilities that once allowed primordial black holes to be the dominant dark matter candidate has been cut down by relentless scrutiny. On the other, the very fact that narrow but viable windows remain is itself remarkable. In science, survival under pressure is meaningful. The hypothesis has not collapsed under the weight of data, as many others have, but continues to live within the gaps, where instruments have yet to fully probe. What emerges most clearly is the role of complementary methods. No single line of evidence is decisive on its own. Microlensing excels at finding objects in certain mass ranges, but falters at others. Gravitational waves reveal mergers of massive objects but depend on assumptions about formation rates. The cosmic microwave background provides exquisite precision, but addresses only particular effects. Stellar dynamics place limits locally, but cannot easily extrapolate across the whole cosmos. Each method has blind spots, but together they form a cross-checking system that steadily narrows the parameter space. This interplay illustrates how modern astrophysics functions. Progress does not come from one definitive test, but from the convergence of many. One of the most intriguing open windows lies around black holes with masses of tens of suns. This range is especially interesting because it overlaps with the masses of many black holes detected by gravitational wave observatories. If even a portion of these mergers involve primordial black holes, then the signals we are hearing are not just stories of dying stars, but echoes from the dawn of time. Some theorists argue that the distribution of detected black hole masses hints at a primordial contribution. Others caution that stellar evolution, especially in environments with very low metal content, can produce similar results. The debate continues, sharpened by each new detection. Another window exists in intermediate mass ranges, between hundreds and thousands of solar masses. These are difficult to probe with microlensing because the events would last far too long for practical observation. They are also not numerous enough to dominate the microwave background constraints. For now, this range remains relatively unconstrained, though future surveys may close it. The very fact that such regions exist keeps the hypothesis alive, like unexplored corners on an otherwise well-mapped continent. It is also worth noting that primordial black holes do not need to make up all of dark matter to be important. Even a modest contribution could have profound implications. They could serve as seeds for supermassive black holes, helping to explain the existence of billion solar mass quasars so early in cosmic history. They could account for a subset of unusual gravitational wave events. They could provide insights into the conditions of the early universe, even if particles supply the bulk of the missing mass. In this sense, the hypothesis is not all or nothing. The legacy of primordial black holes may be significant, even if they are only a fraction of the story. The challenges are clear. To confirm the hypothesis requires unmistakable evidence, such as a microlensing event that cannot be explained by known objects, or a population of gravitational wave signals with properties inconsistent with stellar origins. To refute it requires tightening the constraints until no viable mass windows remain. Both paths demand better instruments, longer surveys, and sharper analyses. That work is already underway, with new observatories preparing to test the surviving possibilities with unprecedented sensitivity. In this way, the search for primordial black holes embodies the rhythm of science itself. An idea is proposed, tested, restricted, but not yet eliminated. Each new observation trims the possibilities, like a sculptor chiseling stone, until either the truth emerges or the hypothesis is reduced to dust. Whether primordial black holes are revealed as the missing matter or are finally excluded, the journey illuminates the power of observation to confront theory. For now, the situation is balanced on a knife's edge. The data neither confirms nor dismisses. The universe remains silent on whether ancient black holes drift unseen in its dark corridors. This ambiguity fuels both caution and curiosity. We must be skeptical, for extraordinary claims demand extraordinary proof. Yet we must also be open, for history shows that the cosmos often surprises us in ways we cannot anticipate. And so we close this chapter at a moment of tension. Primordial black holes have endured a gauntlet of tests, scarred but standing. They remain possible, if only barely, as candidates for dark matter. To weigh the case for them seriously, we must now step back from the evidence and ask whether their properties, known and hypothesized, truly align with what dark matter must be. The time has come to consider the arguments in their favor, before turning to the formidable challenges that stand against them. When considering the identity of dark matter, we must begin with the properties it is known to possess. Dark matter interacts primarily through gravity. It does not emit, absorb, or reflect light in any measurable way. It must be stable over the lifetime of the universe, persisting from the earliest epochs until today. It must clump under gravity to form the scaffolding for galaxies. Yet it must also remain sufficiently diffuse to avoid interfering with small-scale structures in ways we do not observe. These requirements are demanding, but black holes, especially primordial ones, fit them naturally. Black holes are by definition invisible, their event horizons hiding all light that might otherwise betray them. They interact only through gravity, which is precisely how dark matter appears to behave. Unlike exotic particles that require new physics beyond the standard model, black holes require no theoretical inventions. They are a straightforward consequence of general relativity. Objects we already know exist in multiple forms. This alone makes them compelling. To explain dark matter, one does not need to invoke unknown fields or forces. Only a population of objects formed in the right numbers and at the right times. One of the strongest arguments in favor of primordial black holes as dark matter is the overlap with gravitational wave detections. The black holes observed by LIGO and Virgo, often in the range of 20 to 50 solar masses, fall squarely within one of the surviving mass windows, where primordial black holes are not yet ruled out. If a significant fraction of these merging black holes are primordial in origin, then gravitational wave astronomy is not only confirming Einstein's century-old prediction, but also uncovering the very substance of dark matter. The coincidence is tantalizing. Another point in favor is the role primordial black holes could play in explaining the rapid growth of supermassive black holes. Observations of quasars less than 1 billion years after the Big Bang reveal black holes with masses of 1 billion suns. Growing such giants from ordinary stellar seeds in such a short time is difficult. But if primordial black holes provided the initial seeds, already massive at birth, the problem becomes more tractable. Galaxies could have formed around these seeds, and their subsequent accretion of gas would accelerate their growth. In this way, primordial black holes not only explain dark matter, but also solve one of the greatest puzzles in early cosmic history. Black holes also provide a natural explanation for why dark matter has evaded detection in laboratories. For decades, experiments have searched for weakly interacting massive particles, or axions. Despite extraordinary sensitivity, they have found nothing. If dark matter consists of primordial black holes, this failure is no surprise. Black holes do not interact with detectors underground, no matter how sensitive. They cannot be produced in accelerators, no matter how energetic. Their invisibility to such experiments is not a flaw in the hypothesis, but a feature. It explains why dark matter has been so elusive, despite global effort. Furthermore, black holes are stable by nature. They do not decay over cosmic time, except for the very smallest that evaporate through Hawking radiation. Those above a critical mass, however, persist indefinitely. This longevity fits the requirement that dark matter must have survived from the early universe to the present. Their persistence makes them ideal candidates for something that must dominate the cosmos over billions of years. There is also an economy of explanation in the black hole hypothesis. Rather than invoking new physics, primordial black holes arise from processes we already accept: density fluctuations, inflation, and gravitational collapse. They are fossils of conditions we believe were present. This parsimony appeals to the scientific instinct for simplicity. If a known object can explain a mystery, it deserves serious consideration. The cultural resonance of black holes adds another layer. These objects have captured the human imagination like few others. symbols of ultimate mystery and power. To discover that they also hold the key to dark matter would be poetic, uniting two great enigmas in a single reality. While cultural fascination does not prove scientific truth, it underscores why the hypothesis grips so many minds. The idea feels natural because black holes are already icons of the unseen. Still, advocates of the black hole hypothesis must tread carefully. Enthusiasm is not evidence. Yet the alignment of properties, the overlap with observational windows, and the explanatory power for multiple cosmic puzzles combine into a strong case. Primordial black holes can behave like dark matter, explain phenomena particles struggle to address, and remain consistent with constraints in certain mass ranges. They are not ruled out, and in science, survival against long odds often signals that an idea deserves deeper exploration. As we weigh these points, the hypothesis begins to appear not only possible, but attractive. Black holes already exist. They already embody the properties required. They may even be whispering to us through gravitational waves and the ancient beacons of quasars. To dismiss them outright would be premature. Instead, we must ask how strong this case truly is, and whether the challenges against it outweigh its elegance. But before confronting those counterarguments, it is worth pausing to recognize how remarkable it is that known physics provides such a candidate at all. The more one examines the properties of dark matter, the more black holes seem to fit the bill. Consider the way dark matter shapes galaxies. Observations show that stars in the outskirts of spiral galaxies move far faster than expected from visible matter alone. The simplest explanation is a halo of unseen mass that extends beyond the visible disk. Black holes scattered throughout such halos would provide exactly this kind of gravitational glue. They would not shine, they would not collide with ordinary matter in ways we could detect, but their collective gravity could easily bind galaxies together. Primordial black holes also sidestep some of the theoretical problems faced by particle dark matter models. Weakly interacting massive particles, once the favored candidate, were motivated by elegant extensions of particle physics. But as experiment after experiment return null results, their parameter space has shrunk. Actions, another promising candidate, remain possible but elusive. Sterile neutrinos could account for some phenomena, but struggle to explain the full picture. In contrast, black holes require no invention of new particles or forces. They are consistent with general relativity and cosmology as we already understand them. In an era where simplicity carries weight, this parsimony is striking. Another strength of the black hole hypothesis is its ability to explain multiple cosmic mysteries with one idea. Dark matter is the central puzzle, but there are others. Why do we see quasars powered by billion solar mass black holes so early in the universe? Why do gravitational wave observatories detect mergers of black holes heavier than models predict? Why do simulations of galaxy formation work better when assuming compact massive objects in halos? Primordial black holes offer a common thread. They could seed supermassive black holes, account for unexpected gravitational wave populations, and enhance structure formation. While each of these puzzles could in principle be explained separately, the convergence around primordial black holes gives the hypothesis a rare unifying power. Evidence from gravitational wave detections has been especially provocative. Some events show black holes of masses that are awkward to produce by ordinary stellar evolution. For example, stars in certain mass ranges are expected to blow apart in pair instability supernovae, leaving no remnant. Yet gravitational wave signals have hinted at black holes within this forbidden zone. If confirmed, such objects would be difficult to explain by standard astrophysics, but natural in a primordial origin scenario. Each unusual signal therefore becomes a possible clue, a whisper from the early universe carried across billions of years. The survival of narrow mass windows in observational constraints is another reason the case remains alive. While microlensing, cosmic microwave background analysis, and gamma-ray studies have ruled out large portions of parameter space, not all have been eliminated. Tens of solar masses remain plausible. Intermediate ranges, too, have not been fully tested. These surviving corridors are not arbitrary leftovers. They align with some of the most intriguing observational hints such as heavy black hole mergers. The fact that the data both excludes much and yet allows these significant regions suggests the hypothesis deserves continued attention. Primordial black holes also fit naturally into the timeline of the cosmos. If they formed during inflation or shortly after, they would have been present from the very beginning. They would have acted as seeds for structure, helping galaxies form more quickly. Their gravitational influence would have been woven into the universe's history from the start. This is exactly what is required of dark matter, a component that has been present and dominant since the earliest times, shaping everything that followed. Another virtue lies in their invisibility to traditional dark matter searches. Underground detectors that seek faint collisions of exotic particles with atomic nuclei have so far reported nothing. Particle colliders have not revealed any new particles that could account for the missing mass. While this is a frustration for particle physicists, it is consistent with black holes. If dark matter is made of primordial black holes, then no laboratory on Earth would ever capture them. Their evidence would be written only in the sky, in the gravitational footprints they leave behind. The failure of particle searches does not disprove dark matter, but it makes the black hole option relatively stronger. There is also an elegance in the fact that black holes, once dismissed as impossible, now stand as proven realities. Their existence is beyond doubt. To extend their role from astrophysical objects to cosmological actors is not a leap of faith, but a reasonable extrapolation. We already know they are out there, and in large numbers. To suggest that more of them, formed earlier and in different ways, could account for dark matter is not as radical as it first seems. In all of this, one must remain cautious. Evidence in favor is circumstantial, not definitive. Yet the accumulation of consistency is important. Black holes meet every known requirement of dark matter. They explain some puzzling observations. They remain allowed in certain mass ranges, and they require no new physics. These points, taken together, form a case that is difficult to dismiss outright. As the debate continues, it becomes clear that the hypothesis has matured. No longer dismissed as fringe, primordial black holes now stand as a credible alternative to particle dark matter, worthy of careful study. The balance of probabilities remains uncertain, but the argument for their candidacy is strong enough to merit serious consideration. The next step is to weigh these advantages against the significant challenges. For science does not advance by enthusiasm alone. Every hypothesis must face its counter-arguments, and the black hole scenario is no exception. The appeal of black holes as dark matter lies not only in their compatibility with known physics, but also in the way they embody the very essence of the unseen. When astronomers map galaxies, they see vast halos of mass with no light. When they calculate the growth of cosmic structure, they find that something invisible must have been present from the earliest times. Black holes, with their absolute darkness and pure gravitational presence, seem to fit this role almost poetically. One strength of the black hole hypothesis is that it provides a natural explanation for why dark matter has been so elusive. For decades, detectors buried beneath mountains have been waiting for a single particle to collide with an atomic nucleus, a faint trace that would reveal the identity of dark matter. But nothing has come. If the dark matter is made of primordial black holes, this silence is exactly what we should expect. Black holes cannot be trapped in tanks or caught in detectors. They slip past laboratory walls as if they do not exist. Their signature lies only in gravity, in the arcs of starlight, in the ripples of space-time, and in the invisible scaffolding of galaxies. Another point in favor is that primordial black holes are not a speculative extension of theory, but a prediction of conditions we believe actually existed. The early universe was filled with density fluctuations. Inflation stretched quantum jitters across cosmic scales. Collapse was inevitable in some regions. To deny the possibility of primordial black holes is to deny the universe permission to follow its own rules. In that sense, they are not only plausible, but perhaps expected. The real question is whether enough of them formed and survived to make up the majority of dark matter. They also provide an answer to puzzles that otherwise strain credibility. The discovery of quasars less than 1 billion years after the Big Bang remains one of the most striking challenges in astronomy. To grow black holes of 1 billion suns from ordinary stellar seeds in such a short span seems nearly impossible. Yet if primordial black holes provided massive seeds from the very beginning, the problem dissolves. Similarly, the black holes detected by gravitational waves, heavier than expected from normal stellar processes, find a natural explanation if some fraction are primordial. These coincidences cannot be ignored. Even simulations of galaxies gain plausibility when primordial black holes are included. Compact, massive objects in halos can help reproduce observed structures, lending weight to the idea that dark matter need not be diffuse particles, but could instead be discrete objects. The flexibility of the hypothesis to fit multiple domains is one of its most attractive features. There is also the philosophical beauty of solving two great mysteries with one answer. Dark matter and black holes stand as two of the most mysterious phenomena in modern science. To discover that they are linked, that the invisible mass of the universe is composed of the most invisible objects in nature, would be a triumph of elegance. Science rarely grants us such symmetry, but when it does, the results resonate deeply. None of this is to say that the case is closed. Advocates of the black hole hypothesis must admit that the evidence is circumstantial, not definitive. Yet circumstantial evidence accumulates, and the alignment of so many lines of reasoning cannot be dismissed lightly. The possibility remains that the missing matter of the cosmos is not exotic particles hiding in detectors, but ancient black holes drifting silently through space, relics of creation itself. In the end, the argument for black holes as dark matter rests on three pillars. First, they already exist and possess the required properties: invisibility, stability, and pure gravitational interaction. Second, they explain phenomena that otherwise strain models: early quasars, heavy gravitational wave sources, and the failure of particle searches. Third, they remain observationally viable within specific mass ranges. These pillars are strong enough to hold the hypothesis upright, even under intense scrutiny. But science is never satisfied with arguments alone. Every case must face its countercase. For every strength, there is a challenge. For every corridor of viability, there is a wall of constraint. The next chapter will confront these difficulties head-on. It will ask whether the same evidence that makes primordial black holes attractive also reveals their limitations, and whether the balance of data still favors particles over objects. Only by weighing both sides can we approach the truth. Every scientific idea must withstand the tests of evidence, and even the most elegant hypotheses can falter when confronted with data. The notion that primordial black holes could make up dark matter is compelling, but it faces formidable challenges. While they possess the right qualities on paper: invisibility, gravitational influence, and stability, the universe is not so easily persuaded. Observations across the electromagnetic spectrum, from visible light to gamma rays, have placed severe limits on how many primordial black holes can exist. The more carefully we examine the sky, the more difficult it becomes to allow them to account for all of dark matter. One of the most significant challenges arises from microlensing surveys. These experiments, designed to catch the temporary brightening of distant stars as a massive object passes in front, have been remarkably successful at constraining the population of compact dark objects. The MACO project, which operated in the 1990s, initially reported some candidate events that suggested dark compact bodies might contribute to the galactic halo. But later surveys with greater sensitivity, including the EROS and OGLE collaborations, found far fewer events than expected if primordial black holes were the dominant dark matter. The Subaru HyperSuprimecam extended these studies further, eliminating wide swaths of parameter space. While narrow windows remain, the absence of sufficient microlensing events strongly argues against black holes as the majority component of dark matter in many mass ranges. Another obstacle comes from the cosmic microwave background. Primordial black holes accreting gas in the early universe would have injected radiation into the surrounding plasma. This energy would have altered the ionization history, leaving measurable fingerprints in the subtle temperature and polarization patterns of the background. Satellites like WMAP and Planck have mapped these patterns with exquisite precision, and their results leave little room for widespread primordial black holes above certain masses. Too many would have distorted the cosmic microwave background beyond what we observe. This constraint closes off large parts of the mass spectrum that once seemed promising. Gravitational wave astronomy, which at first appeared to support the idea, also imposes limits. While the detection of unusually heavy black hole mergers suggested a possible primordial origin, the overall merger rate is too low to support primordial black holes as the dominant dark matter. If vast numbers of them existed, detectors like LIGO and Virgo would be overwhelmed with signals. Instead, the rate is consistent with stellar populations, perhaps with a slight excess, but not nearly enough to explain all of the dark matter. Thus, gravitational waves both intrigue and restrain the hypothesis. Local dynamics also tell against large numbers of primordial black holes, wide binary stars in the galactic halo, fragile systems that can be disrupted by close encounters, survive in numbers inconsistent with an abundance of massive black holes. Similarly, the internal structures of dwarf galaxies and star clusters show stability that would have been destroyed if dark matter were composed largely of heavy compact objects. These small-scale observations are powerful because they provide natural laboratories where the presence of too many intruders would be obvious. Their absence speaks loudly. High-energy astrophysics adds further complications. According to Hawking's theory, small primordial black holes should evaporate over cosmic time, releasing bursts of radiation as they vanish. If they were ever abundant, their collective evaporation would have left a clear imprint in the gamma-ray background. Observations from the Fermi Gamma-Ray Space Telescope and other instruments show no such excess. The silence of the gamma-ray sky excludes large populations of low-mass primordial black holes, closing off the possibility that the missing matter resides in this realm. Taken together, these constraints are daunting. While narrow gaps remain, the overwhelming majority of potential mass ranges are now excluded. Primordial black holes cannot make up dark matter in the ranges equivalent to planets, small stars, or tiny evaporating relics. What remains viable are only specific corridors, such as tens of solar masses or certain intermediate ranges. This does not eliminate the hypothesis entirely, but it reduces its plausibility. To claim that primordial black holes explain all of dark matter now requires a careful threading of the observational needle, avoiding the walls of constraint on every side. This narrowing also raises concerns about fine-tuning. Why should the universe have produced primordial black holes in precisely the right mass ranges that remain consistent with data? Why not in the ranges already excluded? Science does not favor explanations that require nature to be so delicately arranged. The burden is on the hypothesis to show why those specific masses are natural outcomes of early universe physics. Without such justification, the coincidence feels forced. In addition, there are distribution problems. Dark matter must form smooth halos around galaxies, shaping their rotation and clustering on large scales. But if dark matter were composed of relatively rare, massive objects, its distribution might not produce the observed smoothness. Instead, it could introduce granularity and disrupt delicate structures. Simulations suggest that too many primordial black holes would cause clumping, inconsistent with the elegant halos we infer from galactic dynamics. This granularity problem is one of the most persistent challenges to the black hole hypothesis. Despite these difficulties, the idea is not entirely dead. Some mass windows survive, and some arguments remain in its favor. But the balance of evidence weighs heavily against primordial black holes as the sole explanation for dark matter. The challenges are too numerous and too consistent across multiple observational fronts. What once seemed a natural and elegant solution now appears increasingly constrained. The resilience of the hypothesis lies in its ability to adapt. Proponents now often argue not that primordial black holes make up all of dark matter, but that they may contribute a fraction. Even this reduced claim, however, must confront the gauntlet of constraints. As we turn to the next part of the discussion, it becomes clear that the challenges are not minor obstacles, but fundamental barriers. The difficulties facing the primordial black hole hypothesis deepen when one examines the details of cosmic structure Dark matter is not simply an abstract addition to equations. It is the backbone on which galaxies and clusters grow. Its distribution must be consistent with the large-scale patterns we observe in the universe, from the clustering of galaxies to the filaments of the cosmic web. If dark matter were made primarily of black holes, its discrete and lumpy nature could cause problems. Simulations suggest that if dark matter consisted of relatively massive black holes, their gravitational interactions would disrupt small-scale structures. Dwarf galaxies, the fragile companions of larger galaxies, would be particularly vulnerable. Observations show that these tiny galaxies maintain stable forms and smooth distributions of stars. If they were filled with roaming black holes, their structure would be stirred, heated, and in some cases destroyed. The survival of these systems implies that dark matter must behave more like a smooth fluid than like a collection of discrete massive objects. The problem extends to the galactic halo itself. For galaxies like the Milky Way, the observed rotation curves are best explained by halos of smoothly distributed dark matter. If the halo were dominated by primordial black holes, the distribution would be grainy, with clumps and voids that would create irregularities in stellar motions. So far, no such irregularities have been found. The smoothness of rotation curves across thousands of galaxies is a strong strike against the idea of dark matter composed entirely of compact black holes. Gravitational wave detections add another complication. While LIGO and Virgo have observed dozens of black hole mergers, the rate is far lower than what would be expected if primordial black holes made up all of dark matter. The sky should be alive with collisions, each producing ripples in space-time. Instead, the signals arrive only a handful of times per month. The measured rate matches expectations for black holes formed by stellar processes, perhaps with a few anomalies, but not for a universe saturated with primordial ones. This mismatch between prediction and observation undercuts one of the most exciting arguments once made for the hypothesis. There are also statistical issues with the distribution of detected black hole masses. The mergers observed so far do not show the kinds of peaks or patterns that would be expected if primordial black holes dominated. Instead, the masses and spins align more closely with those produced by stellar evolution, albeit with some surprises. Each new detection tightens these constraints, and as the catalogue grows, the case for a large primordial contribution weakens. On the high-energy front, the absence of gamma-ray signals from evaporating small black holes remains a powerful constraint. If the early universe produced large numbers of low-mass primordial black holes, they should now be in their final stages of evaporation, releasing bursts of radiation. Instruments like the Fermi Gamma-Ray Space Telescope have not detected such events. The diffuse gamma-ray background shows no unexplained excess. This silence rules out a wide range of possibilities and leaves little room for primordial black holes below a certain threshold. The cosmic microwave background, too, remains a formidable obstacle. Any population of black holes massive enough to accrete gas would have left visible scars in the radiation that fills the universe. The absence of such scars is difficult to reconcile with a universe dominated by primordial black holes. Even the smallest distortions would have been recorded by the Planck satellite's sensitive instruments. The fact that the data fits so well with the standard lambda cold dark matter model, without the need for additional contributions, leaves little room for alternative explanations. Another challenge lies in the formation mechanisms themselves. While it is possible for inflationary fluctuations to create primordial black holes, producing them in just the right abundance and mass ranges requires finely tuned conditions. Inflationary models that predict enough primordial black holes to be dark matter often require specific choices of parameters that feel contrived. Nature tends to resist such fine-tuning. If primordial black holes exist, they may well be present in some abundance, but the idea that they account for the majority of dark matter strains credibility. For these reasons, most cosmologists continue to favor particle explanations for dark matter. Weakly interacting massive particles, axions, and sterile neutrinos all remain viable in some form, despite the lack of direct detection. These candidates behave like smooth, collisionless fluids, matching the distribution of galaxies and large-scale structure more naturally than black holes do. They also arise from independent motivations in particle physics, tying dark matter to deeper questions about the nature of fundamental forces. The elegance of these connections keeps them at the forefront of research. Still, the allure of black holes lingers. Their existence is certain, unlike that of hypothetical particles. They are natural products of physics we already know, and they remain consistent with some observational hints. But when weighed against the challenges, the smoothness of galactic halos, the survival of small galaxies, the limited rate of gravitational wave events, the silence of the gamma-ray sky, and the pristine patterns of the cosmic microwave background, the balance tilts away from them as the dominant dark matter. Yet science thrives on testing the improbable, for even when a hypothesis fails, the effort illuminates new paths. The challenges to the primordial black hole hypothesis are not merely obstacles but also opportunities, sharpening our understanding of both black holes and dark matter. They force us to refine our models, question our assumptions, and design better observations. In this way, the struggle against the data is as valuable as any discovery. The persistence of the primordial black hole hypothesis shows the resilience of science in entertaining bold ideas. But the weight of evidence leans against it as the complete answer to dark matter. At its core, the challenge is that dark matter must behave like an invisible fluid spread across the universe, while black holes are discrete, compact objects whose gravitational influence is granular. The smoothness of galactic halos, the stability of dwarf galaxies, and the uniformity of the cosmic microwave background all demand a level of evenness that primordial black holes struggle to provide. This does not mean primordial black holes cannot exist. In fact, many cosmologists suspect that some population of them may be out there, born from density fluctuations in the earliest instance of time. But their contribution to the total dark matter budget is likely limited, perhaps only a fraction rather than the whole. The idea that they could account for 100% of the unseen mass has grown increasingly difficult to sustain. The strongest constraints from microlensing, gamma rays, and the cosmic microwave background now leave only narrow corridors where they remain viable. The mainstream view, therefore, continues to favor particle candidates. Weakly interacting massive particles, though elusive, remain theoretically attractive because they naturally arise in models that extend the standard model of physics. Actions proposed to solve the strong CP problem in quantum chromodynamics offer another elegant path. Even sterile neutrinos, though speculative, could provide a warm form of dark matter that addresses small-scale structure puzzles. While none of these particles have yet been detected, they align more smoothly with the required properties of dark matter in cosmological models. There is also a philosophical dimension to this preference. Dark matter is not simply a placeholder in equations. It represents a fundamental part of the universe, one that likely points to physics beyond what we know. Discovering a new particle would open a new frontier, connecting cosmology with particle physics in a way that would revolutionize both. Primordial black holes, while fascinating, do not offer the same promise of unlocking new fundamental laws. They are extraordinary relics of known physics, not gateways to undiscovered realms. For many scientists, the hope of new physics carries weight alongside the evidence. Another reason for caution lies in the temptation of simplicity. It is seductive to imagine that the most invisible objects we know could also be the invisible matter we seek. The elegance of such an idea can blind us to the complexities of data. Science has learned repeatedly that nature is not obliged to satisfy our sense of beauty. The case for black holes as dark matter is strong in its narrative appeal, but weaker under quantitative scrutiny. The mismatches with observations, the fine-tuning required for their formation, and the difficulties with distribution make the hypothesis fragile. Even so, the debate is valuable. The exploration of primordial black holes has spurred new observations, sharpened our tools, and deepened our understanding of both the early universe and gravitational physics. It has pushed gravitational wave astronomy to consider broader implications, driven microlensing surveys to new levels of sensitivity, and inspired fresh simulations of galaxy formation. In testing this idea, we have advanced science regardless of whether the hypothesis ultimately stands or falls. The lesson here is not that primordial black holes must be dismissed, but that they cannot shoulder the burden of explaining all of dark matter on their own. They may yet play a role as a partial contributor, or as seeds for supermassive black holes, or as rare relics of inflation, but the mainstream picture still requires something more, something that behaves like a smooth, collisionless particle population pervading the cosmos. The failure to detect such particles so far is frustrating, but the absence of proof is not proof of absence. Experiments continue to improve, and the hunt presses on. Thus, the balance of probabilities favors particles over black holes, not because black holes are impossible, but because the data demands consistency that particles provide more readily. The elegance of primordial black holes as dark matter is undeniable, but science is not ruled by elegance alone. It is ruled by evidence, and the evidence points elsewhere. As we leave this chapter, the question remains, if not black holes, then what? The search for dark matter does not end with constraints. It widens into a race among competing candidates, each with its own promise and challenges. Weakly interacting massive particles, axions, and sterile neutrinos all line up as contenders, awaiting either discovery or elimination. To understand why the scientific community continues to focus on these particles, we must turn next to their story, to the experiments built to catch them, and to the hopes and frustrations of the particle dark matter hunt. The mystery of dark matter has always been a race between ideas. If primordial black holes cannot easily explain the invisible mass, then what else could it be? For decades, the leading answers have come not from the heavens, but from the subatomic world, where theories of particles offer candidates that might pervade the universe unseen. These invisible particles would drift through galaxies like a fluid, filling halos with mass yet leaving no light behind. Their presence would be revealed only through gravity, the one force strong enough to betray them. What makes these particle candidates compelling is that they do not arise solely to solve the dark matter problem. Instead, they emerge naturally from unresolved puzzles in fundamental physics, lending them a kind of credibility that black holes alone cannot match. The most famous of these candidates are the weakly interacting massive particles, or WIMPs. Their story began in the late 20th century, when theorists exploring extensions of the standard model of particle physics discovered that many versions of supersymmetry predicted new particles that were heavy, stable, and weakly interacting. If such particles were created in the hot, dense conditions of the early universe, their abundance today would align remarkably well with the amount of dark matter inferred from cosmology. This uncanny coincidence, nicknamed the WIMP miracle, propelled them to the front of the race. For decades, WIMPs were considered not just a possibility, but the most likely answer. The experimental effort to detect them has been vast. Imagine enormous tanks filled with liquid xenon, buried deep underground in abandoned mines, to shield them from cosmic rays. Instruments inside wait for the faintest flash of light or smallest ionization burst that would occur if a WIMP collided with an atomic nucleus. Experiments like Luke's Panda X, Xenon 1T, and now the Luke Zeppelin detector represent engineering at the edge of what is possible, reaching sensitivities that can detect fewer than one false signal per year. And yet, year after year, these detectors remain silent. Each null result carves away another part of the WIMP parameter space. Optimism has turned into patience, but the pursuit continues. The prize is too great to abandon, for if WIMPs exist, their discovery would not only solve dark matter, but also prove that the universe is built on symmetries deeper than those we know. Alongside WIMPs, another candidate has risen, the axion. Its origins lie in a puzzle of the strong nuclear force. Physicists have long wondered why the strong force, which binds quarks into protons and neutrons, does not break a fundamental symmetry, known as CP symmetry. The axion was proposed to solve this problem, a particle so light and elusive, it could have gone unnoticed all this time. Later, scientists realized that if axions were created during the Big Bang, they could form a cold and invisible background throughout the cosmos. Unlike WIMPs, which would be relatively massive, axions would be feather-light, but produced in such huge numbers that their total mass could account for dark matter. Searching for axions requires different tools. The Axion Dark Matter experiment, known as ADMX, uses powerful magnets and resonant microwave cavities to coax axions into converting into photons. The experiment listens like a radio scanning the cosmos, sweeping through frequency ranges one by one. Casper and other projects take different approaches, looking for subtle effects axions might have on nuclear spins or electromagnetic fields. These searches are still in their early stages, but technology is advancing quickly. Each year, experiments reach deeper into the parameter space, and the regions most likely to harbor axions are now within reach. If detected, axions would not only reveal dark matter, but also solve one of the most stubborn puzzles in quantum physics. Sterile neutrinos form a third family of candidates. Ordinary neutrinos, those ghost-like particles that stream through Earth by the trillions every second, are already part of the standard model, but they are far too light to account for dark matter. The idea of a sterile neutrino, a heavier cousin that interacts only through gravity, offers a new path. Sterile neutrinos would belong to the category of warm dark matter, behaving differently on small scales than cold dark matter does. They might suppress the formation of the smallest galaxies, a prediction that could explain why simulations often produce more dwarf galaxies than we see in reality. Hints of sterile neutrinos have emerged in both laboratory experiments and astronomical data. Neutrino oscillation experiments sometimes show anomalies that could be explained by sterile states. Even more intriguing, X-ray observations of galaxy clusters have revealed a faint line at 3.5 keV. Some researchers interpret this as the signal of sterile neutrinos decaying into lighter particles. The interpretation is contested, but if confirmed, it would provide direct evidence of a dark matter particle. Such a discovery would not only solve the cosmic puzzle but also revolutionize our understanding of neutrinos, which already behave in ways the standard model struggles to explain. The comparison between particle candidates and black holes is instructive. Black holes are attractive because they already exist, proven and familiar. They require no new physics, but their granularity makes them difficult to reconcile with the smooth distribution of mass the universe demands. Particles, by contrast, fit smoothly into cosmological models. They spread evenly, form halos, and shape galaxies in precisely the way simulations predict. The problem is that no particle has yet been caught. The universe offers us two paths, one simple and existing, but observationally constrained, the other elegant and theoretically rich, but experimentally elusive. This competition is not just about evidence, but about philosophy. Many physicists favor particle dark matter because it promises more than a solution to one problem. It offers new physics, new forces, and deeper connections. WIMPs tie into supersymmetry. Axions solve the strong CP problem. Sterile neutrinos expand the neutrino sector. Each candidate, if found, would transform physics in ways that black holes would not. Primordial black holes may solve a cosmic riddle, but particles promise to open new chapters of nature's book. Yet the absence of discovery keeps the race open. Each silent detector makes black holes harder to ignore. Each failed axion search leaves room for astrophysical explanations. The universe seems to be keeping its answer just out of reach, forcing us to push both approaches further. This tension is not a flaw, but the essence of science. Competing hypotheses sharpen each other, driving new experiments, refining predictions, and ensuring that when the truth arrives, it will be undeniable. The race for dark matter is far from over. Black holes remain in play, though constrained. WIMPs, axions, and sterile neutrinos remain elusive, though still promising. The mystery endures, a reminder that the cosmos does not yield its secrets easily. But the significance of the race lies not only in the finish line, but in the journey itself, a journey that has already transformed technology, deepened collaboration, and expanded imagination. The next decade of observation and experimentation will determine whether particles, black holes, or something entirely unexpected will claim victory. Until then, the race continues, propelled by curiosity, persistence, and the conviction that the darkness can and will be understood. The search for dark matter is entering a decisive era. For nearly a century, astronomers have traced its presence through the motions of galaxies, the bending of light, and the subtle ripples in the cosmic microwave background. For decades, physicists have hunted for it in underground laboratories and particle accelerators. Yet for all this effort, the identity of dark matter remains hidden. The coming decade promises to be different. A convergence of experiments, telescopes, detectors, and simulations is about to push the mystery to its limits. The universe can no longer keep its secret much longer. Among the most powerful tools are gravitational wave observatories. In 2015, LIGO opened a new window on the cosmos by detecting ripples in space-time from the merger of two black holes. Since then, dozens of events have been recorded, including collisions of neutron stars and black holes of various masses. But these detections are only the beginning. Next-generation facilities, such as the Einstein Telescope in Europe and Cosmic Explorer in the United States, will expand our reach dramatically. They will be sensitive enough to detect black hole mergers across most of the observable universe, recording tens of thousands of events every year. With such a catalogue, scientists will be able to map the distribution of black hole masses, spins, and merger rates in exquisite detail. If primordial black holes contribute to dark matter, their signature will appear in these statistics. Black holes born in the earliest moments of the universe should differ from those formed in stellar collapse. Their spin distributions may be narrower, their masses may cluster in unexpected ranges, and their merger rates may follow patterns distinct from stellar populations. Even more transformative will be the Laser Interferometer Space Antenna, known as LISA. By placing detectors millions of kilometers apart in space, LISA will capture gravitational waves of longer wavelengths than Earth-based detectors can measure. This will open a new frontier: mergers of supermassive black holes, extreme mass ratio inspirals, where a small black hole falls into a giant one, and signals from intermediate mass black holes. If the seeds of supermassive black holes were primordial in origin, LISA could provide the evidence. Its reach will extend across billions of years of cosmic history, tracing the growth of black holes from their earliest beginnings. While gravitational wave astronomy listens to space-time, microlensing surveys will search the sky for the shadowy passage of compact objects. The Vera Rubin Observatory, with its legacy survey of space and time, will photograph the entire southern sky every few nights for 10 years. This will produce a dataset of billions of stars, each observed thousands of times. When a compact object passes in front of one of these stars, the star will brighten temporarily due to gravitational lensing. Such events have already been studied by projects like MACHO, EROS, OGLE, and the Subaru Hyper Suprime Cam. But Rubin will scale the search to unprecedented levels. If primordial black holes make up even a modest fraction of dark matter, Rubin will see their signature in the statistics of microlensing events. If it does not, the remaining parameter space for black holes as dark matter will shrink to almost nothing. The cosmic microwave background will also play its role. Experiments like the Simons Observatory and the next-generation project known as CMBS-4 will measure the relic radiation of the early universe with unparalleled precision. They will test whether primordial black holes injected energy into the plasma through accretion, leaving subtle imprints in the temperature and polarization patterns. The Planck satellite already constrained these possibilities, but the new missions will sharpen the picture further, leaving little room for hidden populations. In addition, the microwave background will probe inflationary models that might have produced primordial black holes in the first place. These observations will not only test the hypothesis directly, but also reveal whether the conditions for their formation were ever plausible. On the particle side, experiments are preparing to reach unprecedented sensitivity. The Darwin project in Europe aims to build the largest dark matter detector ever constructed, using tens of tons of liquid xenon. It will push the search for weakly interacting massive particles all the way to the so-called neutrino floor, the level at which background signals from solar neutrinos blur with dark matter events. If WIMPs exist within the favored mass range, Darwin will almost certainly find them. If it does not, the WIMP miracle will lose much of its remaining plausibility. Meanwhile, axion searches are expanding as well. ADMX continues to listen with increasing sensitivity, while new designs using quantum sensors, resonance circuits, and superconducting magnets probe previously inaccessible ranges. Actions, if they exist, may soon be within reach. Sterile neutrinos are also drawing attention. The X-ray line at 3.5 kilo-electron-volts remains controversial, but upcoming missions and reanalysis of archival data may resolve the question. If the line is confirmed as the signature of sterile neutrino decay, it will revolutionize cosmology. If it vanishes under scrutiny, sterile neutrinos may still exist at other masses but with reduced credibility. Laboratory experiments on neutrino oscillations will also test whether sterile states are required to explain anomalies. Either way, the coming decade will bring sharper clarity. The role of simulations should not be overlooked. Advances in computing power allow cosmologists to model the universe in exquisite detail, testing how galaxies form under different dark matter assumptions. These simulations will help distinguish between cold particle dark matter, warm sterile neutrinos, and compact object models. For example, warm dark matter tends to suppress the formation of small galaxies, while compact objects introduce granularity into halos. By comparing simulations with the real universe observed by telescopes, scientists can discriminate between candidates in ways impossible before. The key to the next decade lies in synergy. Gravitational waves, microlensing, microwave background data, underground detectors, X-ray telescopes, and simulations are not isolated efforts. They will cross-check one another, forming a web of evidence. If multiple methods converge on the same conclusion, the result will be undeniable. If gravitational waves detect a primordial population, while microlensing confirms their presence, and the microwave background shows consistent anomalies, the case for black holes as dark matter will be overwhelming. If laboratory detectors capture particles while astrophysical observations remain silent, particles will win. If neither side produces decisive evidence, then the mystery will deepen, but the constraints will become so strong that new ideas will be forced to emerge. The decade ahead is therefore not only about discovery, but about closure. It is about pushing each possibility to the limit until it stands or falls. For the first time in nearly a century, we have the tools to make decisive progress. Whether the answer lies in the deep silence of underground detectors, the faint hum of axions turning into photons, the fleeting brightening of a distant star, or the whisper of space-time itself, we are ready to listen. The universe has kept its secret long enough. The next decade may finally bring the answer, or it may reveal an even deeper mystery. Either way, the darkness will not last forever. Why does the search for dark matter matter so deeply? Why pour decades of work, billions of dollars, and the creativity of countless scientists into pursuing something we cannot see, cannot touch, and may never capture in a laboratory? The answer lies in the role dark matter plays in shaping the universe, and in the meaning the search itself holds for science and culture. To understand its significance is to recognize that this quest is not only about finding missing mass, but about confronting the limits of human knowledge. At the most basic level, dark matter is the scaffolding of the cosmos. Without it, galaxies would never have formed. The delicate ripples in the infant universe recorded in the cosmic microwave background would have faded away, leaving behind a diffuse sea of gas. Dark matter provided the gravitational glue that amplified those ripples, pulling ordinary matter into filaments and clusters, creating the conditions for stars, planets, and eventually, life itself. To identify what dark matter is means to understand the origin of structure, the architecture of galaxies, and the destiny of the universe. It is not a detail of cosmology, but its foundation. The search also matters because of what it implies for physics. If dark matter turns out to be a new particle, It will prove that the standard model is incomplete. It will open a door into realms of physics we have long suspected exist but have never touched. Weakly interacting massive particles connect to supersymmetry, a symmetry that could unify forces and explain the hierarchy of masses. Actions not only account for dark matter, but also solve the strong CP problem, a puzzle at the heart of quantum chromodynamics. Sterile neutrinos would expand our understanding of one of the most enigmatic families of particles, reshaping neutrino physics entirely. Each of these discoveries would rival the breakthroughs of the past century, from the discovery of quantum mechanics to the revelation of relativity. If, on the other hand, dark matter is composed of primordial black holes, the implications are equally profound. It would mean that gravity alone, acting in the earliest fractions of a second after the Big Bang, was able to carve relics that still shape the cosmos today. These black holes would be fossils of creation, physical evidence of conditions we can otherwise only infer from theory. To confirm their existence would bridge cosmology and astrophysics in a way no particle ever could. It would show that the universe is capable of surprises that lie entirely within known physics, that sometimes the most extraordinary mysteries are explained by the objects we already understand, but in roles we never imagined. Beyond the scientific stakes lies the cultural meaning of the search. Dark matter has captured the public imagination as a symbol of the unknown. The idea that most of the universe is invisible resonates with a long human tradition of mystery. We have always been drawn to what lies beyond sight, whether in the depths of the ocean, the vastness of the night sky, or the hidden corners of the mind. Dark matter embodies that instinct, reminding us that even in an age of satellites, colliders, and precision cosmology, the universe remains a place of wonder. Black holes, too, carry cultural weight as emblems of the unknowable. To discover that these two mysteries are one and the same would be a story of symmetry and poetry, as well as science. The search also demonstrates the method of science at its best. Hypotheses are proposed, tested, and refined. Weakly interacting massive particles once seemed inevitable, but decades of null results have humbled expectations. Primordial black holes were once dismissed, but new data revived them. Each candidate rises and falls with evidence, not preference. This process may appear slow, but it is what ensures the integrity of science. The willingness to live with uncertainty, to resist the temptation of premature answers, is what separates science from belief. The dark matter search is therefore not just about solving a puzzle, but about practicing the discipline of skepticism. Patience is another lesson. Some discoveries take a century. Gravitational waves were predicted by Einstein in 1916 and detected in 2015. The Higgs boson was theorized in the 1960s and confirmed in 2012. Dark matter may demand the same persistence. The absence of answers today does not mean failure. It means the question is hard, and that we are willing to endure the difficulty until truth emerges. This patience reflects both humility and determination, a recognition that nature reveals itself on its own terms. The search also drives innovation. The technologies created to detect dark matter push the boundaries of engineering and physics. Cryogenics, quantum sensors, superconducting magnets, and underground shielding have all advanced because of this pursuit. Even if dark matter remains hidden, these tools enrich science and industry, providing spin-offs that benefit society. The search is therefore not wasted effort, but an engine of progress. In the end, the significance of the search lies in what it says about our place in the cosmos. We know that most of the universe is invisible, and yet we have built instruments capable of sensing its pull, mapping its influence, and chasing its identity. This is a reminder of both our ignorance and our ingenuity. We are small creatures on a small planet, but we have stretched our minds and our machines to grapple with mysteries that span billions of light years. The fact that we do not yet know the answer is less important than the fact that we are asking the question. To search for dark matter is to confront the unknown without fear. It is to accept that the universe is larger, stranger, and richer than we can yet imagine. Whether the answer is particles, primordial black holes, or something beyond both, the search itself enriches us. It teaches humility, perseverance, and wonder. It shows that science is not only about answers, but about the pursuit of truth wherever it leads. The darkness remains, but it is a darkness filled with possibility, waiting for the light of discovery. For nearly a century, dark matter has haunted cosmology like a shadow behind every observation. We can measure its gravity, trace its influence, and map its distribution across billions of light years. Yet we cannot say what it truly is. We know it outweighs ordinary matter by more than 5 to 1, that it sculpts the great cosmic web, that without it, galaxies could not have formed, and that stars and planets like ours would never have come to be. Its presence is undeniable, and yet its identity remains hidden. After decades of searching with some of the most ambitious experiments ever conceived, we remain still in the dark. The idea that black holes might provide the answer is captivating because it appeals to simplicity. Black holes are already real, observed across the universe, in many forms. Stellar collapse produces black holes of a few to dozens of solar masses. The hearts of galaxies host supermassive black holes with millions or billions of solar masses. Intermediate varieties are being uncovered. Their invisibility, stability, and gravitational power align neatly with the requirements of dark matter. In theory, a population of primordial black holes, born in the first moments after the Big Bang, could account for the unseen mass. They would require no exotic new physics, no untested particles, only the workings of gravity and density fluctuations in the young universe. For a time, this hypothesis shone brightly. The detection of unexpectedly heavy black hole mergers by LIGO hinted at a primordial origin. The puzzle of quasars appearing so early in cosmic history seemed to demand primordial seeds. The elegance of black holes as both enigma and answer resonated. But science does not rest on elegance alone. Observations began to challenge the idea. Microlensing surveys failed to find enough events to support black holes in most mass ranges. The smooth glow of the cosmic microwave background showed no distortions from accretion onto black holes in the early plasma. The gamma-ray sky remained silent, with no evidence of evaporating relics. Gravitational wave catalogues, once thought to favor primordial populations, settled into rates explainable by stellar evolution. The corridors of possibility narrowed until only thin slivers remained. Black holes may still contribute to dark matter, but the dream that they are the entire answer now seems unlikely. On the other side of the race stand the particle candidates. Weakly interacting massive particles dominated theory for decades. Their abundance matched cosmological requirements almost too perfectly, a coincidence dubbed the WIMP miracle. Vast underground detectors filled with liquid xenon or argon were built to catch them, waiting for a faint flash of light from a single collision. The silence has been deafening. With each null result, the most favored ranges for WIMPs shrink. Actions, born from an attempt to solve the strong CP problem in nuclear physics, remain viable, their searches expanding into unexplored ranges, with resonant cavities and quantum sensors. Sterile neutrinos, heavier cousins of known neutrinos, hover on the boundary of possibility, hinted at by anomalies, and a faint X-ray line, but never confirmed. These candidates remain alluring, but like black holes, they too live on the edge of absence. Thus, the paradox of dark matter, at this moment, is profound. The simplest astrophysical candidate is heavily constrained. The most elegant particle candidates remain invisible. The mystery resists both the obvious and the ingenious. To be still in the dark is not to be lost, but to stand at the frontier, confronting the limits of what we know and testing the strength of science itself. This unresolved state is not failure, it is proof of rigor. Science advances by rejecting what does not fit, by refusing to accept stories without evidence, by demanding that even the most beautiful idea must survive the harshness of data. The absence of discovery does not mean the search is pointless. Every null result narrows the field, sharpens our models, and brings us closer to the truth. Each silence is a form of knowledge. The search has also driven extraordinary progress. Gravitational wave astronomy now listens to the universe in ways once thought impossible. Surveys like those from the Vera Rubin Observatory will track billions of stars, providing a treasure of data far beyond dark matter alone. Underground detectors push the limits of shielding, cryogenics, and quantum sensing. Simulations of galaxy formation grow ever more realistic, revealing the fine interplay between visible matter and the invisible mass. Even if the final answer still eludes us, the journey has already enriched science immeasurably. There is humility in this pursuit. The universe does not bend to our expectations. The WIMP miracle was not inevitable. The symmetry of black holes as the solution was not guaranteed. The truth may be stranger than either, perhaps involving new physics we have not imagined, or a mixture of answers, some dark matter as primordial black holes, some as particles, some as something else entirely. The lesson is that nature is under no obligation to satisfy our sense of beauty. It will reveal itself on its own terms. Patience is required. Einstein predicted gravitational waves in 1916, and they were detected almost 100 years later. The Higgs boson was theorized in the 1960s. Discovered in 2012, dark matter may demand the same endurance. The answer may come tomorrow, or decades from now. The waiting is not empty, but filled with progress. Each constraint, a step toward clarity. Yet the significance of the search is larger than the answer. It shows how science faces the unknown, with skepticism, persistence, and imagination. It shows the value of global collaboration, of telescopes, detectors, and simulations spread across continents. It shows that the pursuit of truth requires not only brilliance but humility, not only creativity but discipline. The darkness is not a void, but a frontier, an invitation to explore. As we close this chapter, we must accept that we are still in the dark, but this is not despair. Darkness is where discovery begins. The unseen mass of the universe remains hidden, but we know it is there, pulling the stars, shaping the galaxies, binding the cosmos together. We have built machines to listen to space-time, to count photons from the dawn of time, to trap invisible particles in underground tanks. The silence so far is not the end of the story, but the tension before revelation. When the answer comes, it will be more than a solution to a puzzle. It will be a transformation of our understanding of reality. If it is a particle, we will open a new chapter in physics. If it is black holes, we will link the infancy of the universe to the giants we see in galaxies today. If it is something else entirely, then we will learn that the cosmos is stranger than we ever imagined. In all cases, our picture of the universe will never be the same. To search for dark matter is to embrace mystery as fuel. It is to acknowledge that the majority of the cosmos is hidden, and to commit to the pursuit of bringing it to light. We are still in the dark, but the darkness is alive with possibility. The journey itself, the act of reaching beyond what we know, is as meaningful as the destination. The universe holds its secrets tightly, but history shows that persistence always pries them free. And when the secret of dark matter is revealed, it will remind us once again that our small species, on a small planet, has the courage to seek the invisible and the patience to wait until the universe finally whispers its truth.